Hello and welcome. My name is Haiping Zhao from Chair of Pervasive Computing Systems at Karlsruhe Institute of Technology in Germany. In this talk, I will introduce you the aging-aware training of printed neuromorphic circuits. This is joint work with my colleague Michael Heffenbrock, Michael Weigel, and Mehdi Taoui from Chair of Dependable Nanocomputing, also at Karlsruhe Institute of Technology. Neuromorphic computing refers to computing method inspired by human neurons. In neuromorphic computing, the main operations are weighted sum and nonlinear transformation. Due to the simplicity of these operations, this computing unit can be easily synthesized by circuits. This figure shows a schematic of an electronic neuron consisting of a crossbar for weighted sum operation and a tanh-like nonlinear transformation as the activation function. By interconnecting multiple neurons, powerful nonlinear expressiveness can be achieved. And moreover, the neuromorphic circuits can be designed using a learning-based approach by means of the artificial neural network, which ensures the high efficiency of the designing process. Together with the emerging printed electronic technology, printed neuromorphic circuits acquire additional advantages such as flexibility, ultra-low production cost, and non-toxicity, and so on. This is a photo of multiple printed neurons from our team. In this work, we address another problem of the printed neuromorphic circuits, namely the aging of printed resistors. With the aging effect, the resistance of printed resistors will change over time, as shown in this figure. And therefore, the computing results from the printed neuromorphic circuits will deviate from the designed values. To mitigate this influence, we propose the framework to consider the aging into the design process of the printed neuromorphic circuits. In order to take the aging effect into account, we first build the mathematical aging model of the printed resistors. More specifically, we printed 6 resistors and measured their conductance over 37 days. This figure shows the measurement of the experiment. By observing the aging behaviors, we found that the aging consists of 2 stages, namely a fast degradation phase followed by a gradual phase. This phenomenon is also similar to other works. To build the aging model of printed resistors, we first normalized the measurements by their initial values, as shown in this figure. Subsequently, based on the tendency of the aging behaviors, we selected the exponential function form to describe the aging decay. We also want to highlight that there might be some slight shortcomings in this process. For example, we only printed 6 resistors for the measurement, and the exponential function form might not be the best one. However, they are already presentational for the aging behavior, and more important, the methodology itself is correct. That means the researchers can do experiments with more resistors, and they can also select other functional form for the aging model. But all these modifications can be easily integrated to this framework without any changing in the methodology. We also noticed that even with the same initial conductance, printed resistors have different aging decay. To respect this, we built the stochastic aging model where the omega in the aging model is treated as a stochastic variable. The probabilistic distribution of omega can be extracted from the measurements. Rather than normal distribution, we use the log-norm distribution to keep the sign of omega to be positive. In this way, we can generate stochastic aging curves by sampling stochastic omega from the extracted distribution, and this figure shows multiple generated aging curves. After build the aging model, we modify the objective function of the aging-aware training for printed neural networks. At the very beginning, there is no aging being considered. In this case, the learnable parameter is the surrogate conductance theta, which is related to the conductance to be printed. In this case, the objective is to minimize the loss function on a certain dataset. We refer to this non-aging aware training as nominal training. When we take the aging effect of the printed resistors into account, the conductance is then considered as a variable of time t. In this case, the objective is no longer to minimize the single value of the loss function, but to minimize the loss function over the whole lifetime of the devices. That means we minimize the expected loss with respect to time. However, the learnable parameter theta t in this context is a whole aging curve, which is not a value but a function. This is hard to be optimized by the gradient-based method. Built upon our aging model, the initial conductance theta 0 becomes the learnable parameter, which is no longer a function of time. This facilitates the training of printed neural networks. Moreover, we also respect the stochastic variable omega in the aging model. In this case, the objective function is not only the expected loss with respect to the whole device lifetime, but also the variance of the stochastic omega in the aging model. And this formula is the final objective function in the aging-aware training of printed neural networks. Since the objective function is an integral function, it is still problematic for the gradient-based optimization. Therefore, we employ the Monte Carlo approximation to estimate the integration by addition. In the next slide, we will visualize the process of aging-aware training. In each training epoch, we first sample multiple stochastic aging curves for each learnable conductance. Due to the aging of the conductance, the corresponding weights will change. This figure shows an example of a two-dimensional weight plan. Different stochastic aging behaviors are embodied in different aging trajectories. The expected loss of all the possible trajectories will be considered in the training. But to explain the training process more clearly, we take only one trajectory as an instance. And this figure gives an exemplary loss function. The optimization result of the aging-aware training and nominal training based on this loss function and this aging trajectory is shown in this figure by the red points. We can see from the figure that the result from the nominal training, which is indicated by the blue curve, has the lowest loss value at the initial point. But with the aging, the loss value goes rapidly higher. In contrast, the initial value from aging-aware training is higher than that of the nominal training, but on the whole aging trajectory, the loss values stay low, and thus the expected loss becomes lower than that of the nominal training. To test the effectiveness of the proposed aging-aware training, we conduct experiments on 13 benchmark datasets. We perform both nominal training and aging-aware training for printed neural networks respectively, and we perform the training 10 times with different randomnesses vary from 0 to 9. All the training are normalized time slot from 0 to 1, but in the evaluation, we extrapolate the time slot from 0 to 10. As the evaluation metric, we use the measuring-aware accuracy, which is a hardware-related metric. For this, we can imagine that the output voltage is connected to LEDs. If and only if the output can enlighten the correct LED, the classification is evaluated as correct. Moreover, we also calculate the result of the random guess as the baseline. This is the result of the experiment where the red curves and the areas indicate the measuring-aware accuracy and the standard deviation from the agent-aware training, and the blue one are from nominal training. The black dashed line indicates the random guess. We can find that the performance from nominal training is high at the beginning, but it decreases with the aging. In contrast, the performance from agent-aware training stays in a high level in the whole device lifetime. Moreover, the standard deviation from agent-aware training is also lower than that from the nominal training, which means the performance from agent-aware training is more robust. From our intuitive estimation, the performance from nominal training should outperform agent-aware training at the very beginning, but decrease rapidly caused by the aging effect. However, we also find that the result of agent-aware training on some datasets even outperform nominal training at the beginning. To this, we speculate that this is possibly due to the favorable optimization dynamics through the Monte Carlo sampling. For example, since the agent-aware training samples and calculates gradients for several sets of parameters in the vicinity of the current solution, it might have an easier time escaping from local minimum.